Good morning. I'm Wes Kramer from NRAO. I lead the front-end concept development for the NGVLA. I'll be first covering an overview of the front-end subsystem, and then after that I'll go into some specifics about some of the areas of development that are ongoing. First, the overview. The front-end system has 6 receiver bands housed in 2 cryostats covering 1.2 to 116 GHz with a gap between 50 and 70 GHz. Bands 1 and 2 are 3.5 to 1 bandwidth wideband receivers and feeds. Bands 3 through 6 are waveguide bandwidth 1.7 to 1 bandwidth receivers. All are cooled along with the feeds. The 2 cryostats along with the integrated receiver downconverter digitizer modules are stored in a receiver enclosure. A smaller enclosure called the auxiliary enclosure contains support electronics and the vacuum pump. Total mass of both enclosures is approximately 730 kilograms. Briefly, the block diagrams. These are conventional receivers, all analog. No down conversion stages, just amplification. The band 1 receiver has a 80 Kelvin feed horn. It's anticipated that we won't be able to cool it any more than that because of the high radiation loading through the large window. The band 2 we anticipate cooling to 20 Kelvin, and the LNAs in both of these would be cooled to 20 Kelvin. It also has a noise coupler for calibration purposes ahead of the LNA. This is an area of development for both bands 1 and 2 because of the higher relative losses of these wideband coaxial components. The bands 3 through 6 receivers are pretty much the same, with the exception of an inclusion of an OMT to convert the waveguide input from the axially corrugated feed horn into the 2 polarizations. Otherwise, it's pretty much the same. They're all cooled to 20 Kelvin. The band 1 receiver is housed in a separate dewar. It's based on a feed design by Caltech, a quadridge feed horn cooled to 80 Kelvin with coaxial LNAs cooled to 20 Kelvin. Uses a single Model 350 Gifford-McMahon crowd cooler, run at variable speed for optimum efficiency, and has an approximate total mass of about 74 kilograms. One element not shown in this rendering is the dome. This is envisioned to be a semi-domed quartz fabric window and radome. The second dewar, referred to as dewar B, contains the remaining 5 receivers. These are bands 2 through 6. They're aligned on a lateral axis with a lateral positioner for band selection, with the phase centers aligned on a single axis. The receivers are modular for easily manufacturing and replacement. The entire dewar uses a single GM crowd cooler, similar to the one for dewar A, and the approximate total mass is 89 kilograms. These are some current estimates of the front-end noise performance of the receiver. What's noticeable is the bands 1 and 2 receiver temperatures are slightly higher. This is because of the added loss of the wideband couplers that are used in front of the LNA, and this is an area that we'll be doing more development on that I'll speak to later. There's also a little bit more of an elevated noise temperature in the band 1 due to the choice of LNA that's used from the reference design. We anticipate that will improve as well as we use customized LNAs for these bands. A plot of the sensitivity of a single 18-meter antenna. This is A over T, and as expected, it drops with elevation angle and also with frequency. The drop at the low frequencies is due to the higher spillover of the chosen feed, the current selected feed for band 1, and this is an area that we're looking into as well on the low frequency feed. The sensitivity is fairly optimal for the other bands. They do roll off because of the increased sky temperature, receiver noise temperature, and the effect of surface roughness at shorter wavelengths on the aperture efficiency of the optical system. Next, I'm going to touch on some design and development tasks that were underway leading up to CODR. First, wideband feed horn development for bands 1 and 2. Also, antenna optics and feed horn design optimization for the higher frequency bands. Vacuum and window radome development for all bands. Specifications and simulated performance for the critical components in the receiver, the LNAs, OMTs, and couplers. A more rigorous cascaded analysis than was done before for noise, gain, and dynamic range for all bands. And finally, a detailed 3D mechanical model at more to the component level for both cryostats. There were 2 wideband feed studies conducted in parallel last year, specifically for band 2. The first was led by Robert Lemencic at EMSS, and this was to look at an all-metal quad-ridged feed horn design with an analytic ridge and horn profile. There was a lot of optimization done to determine the design space and limits of this analytic profile, and the end result was a feed that did have good spillover characteristics and cross-pole, acceptable return loss over the band. The efficiency at the lowest frequency was quite good, but it did show some roll-off with frequency. There will be a follow-on study this year to investigate improvements to this feed design, including looking at non-analytic spline profiles like the Caltech horn in order to try to improve the high-frequency aperture efficiency. The second feed study was undertaken by CSIRO and led by Alex Dunning. It was derived from the Parkes ultra-wideband feed design, the 6:1 feed that he developed for that telescope. This was also concluded last year. The main features of this feed are that it uses dielectric loading in the feed, a Teflon dielectric that's 2-part with graded epsilon R, also an extra set of outer corrugations to improve the low frequency response, and a polystyrene foam window and IR barrier. The OMT is also integrated with single-ended outputs and coaxial outputs. Performance of this feed is quite good. It's minimum 85 to 89% aperture efficiency with NGVLA6 optics, fairly uniform with only slight variation. Spillover also very good, 8.5 Kelvin or less. Crosspole better than 25 dB and return loss better than 17 dB. And I'll add that this is the design that we currently have as a placeholder for band 2. The wideband feed used for band 1 is unchanged from the reference design. It's the quad-ridge feed horn from Caltech. This was originally done for the SKA prototype. Has a 58-degree opening angle, slightly larger than NGVLA, and a highly optimized spline profile to maximize aperture efficiency over the full bandwidth. It does have high aperture efficiency uniformly, up to 3.5 gigahertz, between 74 and 80% with SKA optics, and possibly a few percent higher for NGVLA6. It's also very compact. It's one of its best attributes, and very lightweight. It's only 1.4 wavelengths at the aperture at 1.2 gigahertz and is readily scalable to higher frequencies. The main drawback is a backlobe in the response. This causes an elevated spillover noise contribution, especially at the low frequencies. Shielding around the body of the feed and the aperture outside the dewar can reduce this in half, but still it's a problem. And affects the overall sensitivity of the receiver adversely. The input match is somewhat worse than the other band 2 feeds, and we've also noticed cavity mode resonances from tests of the prototype receiver, probably due to the effect of the dewar around the feed. We'd like to investigate a dielectric loaded alternative to this, but this is still TBD. In addition to the feed work, there's also another design study underway currently at EMSS to investigate the antenna optics and optimize the sensitivity of the overall system with the receivers that we have, and also with the axially corrugated feed design that we've picked. There'll be an optimization of both the feed design with the optics to maximize A over T. That design will then feed into a re-optimization of the low frequency feeds to obtain optimum sensitivity at those bands. On vacuum windows, we are in a collaboration with the Green Bank Observatory, with Steve White and Bob Simon. They are developing a semi-domed quartz window for the GBT ultra-wideband receiver, which is a very, very similar type of window that we would like to try with band 1, being a similar construction and frequency. This material has high strength. It's good UV and impact resistance properties. It's quite thin, so we should have low loss and low reflection. And it's right now in the fabrication and testing stage for the ultra-wideband receiver. Probably sometime a little later this year, they'll be able to build a domed window for the Caltech Band 1 prototype, which is already in Green Bank and has been tested. They'll retest with this window to check its vacuum properties and look at the noise contribution and quantify that from this window. For bands 3 through 6, we'll likely use a solid quartz or ultra-high density polyethylene window for low loss, low gas permeation, and good strength. A collaboration with NAOJ is likely in this area. They have extensive experience from ALMA, bands 1 and 2+3, on the design, simulation, and re-optimization of the feeds and windows as needed. Low noise amplifiers, we would prefer monolithic amplifiers for lower production cost and reliability. These have performance that is comparable to traditional discrete chip and wire LNAs. The low noise factory in Sweden is a well-known source for indium phosphide mimics, and they have verified that they can source LNAs for all of our frequency bands. They may need to do some minor redesign to some of their stock models to better optimize the noise performance and packaging. One area of difficulty is our gain flatness requirement, which we may have to revisit in order to avoid an extensive redesign of some of their amplifiers. In addition to low noise factory, another possible source for, in particular, band 6 would be the NGC 35 nanometer process mimics, which were also developed for ALMA bands 2+3. The orthomotive transducer is a key component in bands 3 through 6, and I won't say too much about this because Alvaro is going to give a talk about this shortly. But basically, we'd like to use the same OMT. It's a modified BOIFO double ridge waveguide junction, and very compact, low loss, with excellent match. It's readily manufacturable, either with CNC machining or possibly 3D printing in the future. And their design is directly applicable to NGVLA Band 6. They are in the process of working on possible versions for the other waveguide bands 3 through 5. Couplers for cal injection are a key element in the receiver, and as such must have very low loss in order to avoid compromising the sensitivity of the receiver. Bands 1 and 2 use a require a wideband coaxial strip-line coupler. It's difficult to find units that have low loss off the shelf, so one area of investigation in this phase will be to look at low loss dielectrics and compact designs, possibly even using superconducting films to reduce the conductor loss as much as possible. For bands 3 through 6, the waveguide bands, we have a crossguide coupler that's used in several EVLA high-frequency receivers that can be adapted for use for the NGVLA. It's very compact, and it can be produced in quantity. with some design changes and some development. Receiver cascade analysis, we would like to do a better, more detailed analysis for the conceptual design phase. In addition to cascaded noise and gain, we'd like to look at dynamic range, gain, ripple, and slope, as well as import full S-parameter component data, either measured or simulated. And this is best done with commercial software or a custom package built from Simulink. And this is in process right now. The current way we do this is with Excel. It's relatively easy to do, but very cumbersome for more than just a few frequencies, so we'll be moving away from that in the future. Finally, the mechanical modeling of the cryostat. We've been working on 3D detailed models of all elements inside the cryostats, partly to do accurate cryogenic load analysis to see where we are in terms of power consumption, also to accommodate the feeds and prepare for, have a good starting point for jump off of the preliminary design phase. And that concludes my talk.